Here we're going to calculate an interesting sum. So we're going to look at the sum as n goes from 0 to infinity of n factorial quantity squared divided by 2n that quantity factorial. So maybe in a calculus 2 type class you would be asked to see if this converges or not, and we'll actually get convergence by way of finding the exact sum. But if you want to check that kind of on your own, I think maybe your best bet would be the ratio test. And we know it's the ratio test because we've got these factorials all over the place. And factorials and the ratio test usually go hand in hand when you're testing series. I think there are two unexpected things about this series. First of all, it converges in the first place because we've got this n factorial squared in the numerator, which is huge. But that means that this 2n quantity factorial in the denominator gets even bigger. And then the value that it converges to is also a little bit interesting. Okay, so we're going to use three tools as we calculate the value of this sum. The first one is rewriting each summand as the reciprocal of something called a central binomial coefficient. So we've got n factorial squared over 2n factorial is equal to 1 over 2n choose n. And like I just said, this 2n choose n is sometimes known as a central binomial coefficient. The next thing that we'll show is that the integral from 0 to pi over 2 of the 2n plus first power of sine is equal to 1 over 2n plus 1 times 4n over this 2n choose n. And then finally, we're going to prove this following Maclaurin expansion of arc sine of x over the square root of 1 minus x squared. And we'll get to that, in a bit. Okay, so let's go ahead and start with this first tool and see how that goes. So we're going to go ahead and start with the right-hand side. So here we have the right-hand side of this is 1 over this central binomial coefficient. But now since n is a natural number, that's kind of implicit in the fact that we're taking this sum as n goes from 0 to infinity. I guess a natural number including 0. We can rewrite this as 1 over 2n factorial, quantity factorial I should say, and then n factorial 2n minus n factorial. So actually we're pretty much home free because 2n minus n is obviously n. And then we have 1 over all of this, which means when we flip everything around, we have n factorial times n factorial over 2n quantity factorial, which is exactly what we needed to show. Now we're going to move on to the second tool, which allows us to write something involving this central binomial coefficient as an integral of an odd power of sine. So we're going to prove this by induction. So our base case will be the case when n equals 0. So in other words, we want to look for the integral from 0 to pi over 2 of sine to the first power theta d theta. And that's because if we set n equal to 0 here, we get 2 times 0 plus 1, so that's just 1. But now this is not too hard. The antiderivative of sine is negative cosine theta. And then we need to evaluate that from 0 to pi over 2. Now I can go ahead and switch the order of this evaluation if I change the sign out here. And that's actually helpful in this case because cosine of 0 is 1 and cosine of pi over 2 is 0. So we have this is 1 minus 0, which is equal to 1. But now we want to make sure that that is in this form down here. But notice we can write 1 as 1 over 2 times 0 plus 1 times the quantity 4 to the 0 over 0 choose 0. So all of the components of that product and quotient are equal to 1, so we get a 1 here, which means our base case is satisfied. This formula holds for n equals 0. So the induction step's going to take up a little bit more room than we have left, so I'll go ahead and get rid of this and we'll look at the induction step. So now that we're done with our base case, we need to look at the induction step. In other words, we need to make an induction hypothesis and then prove that that induction hypothesis, possibly with the base case, will give us the next case of this identity. So our induction hypothesis will be that this formula is true for n equals k, and k is bigger than or equal to 0. So let's just write, suppose this is true for n equals k, which is bigger than or equal to 0. And then from there, what we want to do is consider the k plus first case. So, and consider the k plus first case. And we need to show that that case will follow from the kth case. And the k plus first case will be the integral from 0 to pi over 2 of sine to the 2k plus 3 theta d theta. And we can see that because if we plug k plus 1 where we see n here, we'll get 2k plus 2 plus 1, which is 2k plus 3. So that's exactly what we have. Now we want to split this up into parts and use the integration by parts formula. So what I will split this up into will be sine of 2k plus 2 theta times sine of theta d theta. That gives me a hint that perhaps I'll use this as my u and this as my dv in the integration by parts formula. But now I need to calculate du. So notice du, by taking the derivative of this term via the chain rule, we'll get 2k plus 2 times sine of 2k plus 1 theta times cosine of theta. Again, that cosine theta is because of the chain rule. Recalling that the derivative of sine is cosine. And then since dv is equal to sine theta d theta, we see that v will be the antiderivative of sine, but the antiderivative of sine is minus cosine theta. Great. And now let's just recall the integration by parts formula says the integral of u dv is equal to u times v minus the integral of v du. So these are the parts that we want to insert into this formula right here. So let's go ahead and do that. So we're going to have this is equal to u times v. So notice that will give us minus sine 2k plus 2 theta times cosine of theta. This is a definite integral, so we need to evaluate from 0 to pi halves. And then we'll have minus the integral v du. But notice this minus sign will cancel with the 1 inside of v. And we can furthermore take this 2k plus 2 out because it's a constant. So that gives us 2k plus 2 times the integral from 0 to pi over 2. Let's see what we have here. It'll be the sine of 2k plus 1 times the cosine squared. So sine 2k plus 1 theta cos squared theta d theta. Great. Now the next thing that I want to notice is that if we plug pi over 2 into cosine, we get 0. If we plug pi over 2 into sine, we get 1. If we plug 0 into sine, we get 0, and cosine is 1. So both of the upper and lower bounds here inserted into this function will give us 0. So all of this just cancels out to 0. Great. And now next, I notice that I can take this cosine squared and write it like 1 minus sine squared theta. And that may not seem super helpful, but when I take that sine squared and multiply it by the sine 2k plus 1, I will re-achieve my original integral, which will be helpful. So let's go ahead and do that. So I'll bring this down. So this is going to be equal to the quantity 2k plus 2 times the integral from 0 to pi over 2 of, so we'll have sine 2k plus 1 theta d theta minus the integral from 0 to pi over 2 of sine 2k plus 3 theta d theta. And let's put some parentheses around this. So what I did here is distributed this sine 2k plus 1 onto the 1 and the sine squared and then split it up into two integrals. Great. And now, maybe just for notational convenience, let's go ahead and set this integral equal to I sub k plus 1 because it's the k plus first case. And notice that here we have achieved I sub k plus 1 again because it's the k plus first case. So that gives us an equation that we can solve for I sub k plus 1. So notice I've got 2k plus 2 copies of that integral on the right-hand side and a single copy on the left-hand side. And I should say that these 2k plus 2 copies are negative. So when we move that over, we build the following equation. So we'll have 2k plus 3 copies, again because we've got 2k plus 2 on the right and 1 on the left, so we add those together, we get 2k plus 3. And then I'll just write this as I sub k plus 1 So that's going to be equal to 2k plus 2 times the integral from 0 to pi halves of sine of 2k plus 1 theta d theta. But then our induction hypothesis tells us the value of this integral because we supposed that this formula was true for n equals k. So we can just insert the right-hand side of this equation with n equals k for that integral. So that gives us 2k plus 2 times, let's see what we have. We have 1 over 2k plus 1 times 4 to the k over the central binomial coefficient 2k choose k. Great. So I'll rewrite this equation that's red underlined at the top of the next board, replacing I sub k plus 1 with this integral, given the fact that we'll have more room. So on the last board, we achieved the following equation involving the k plus first case of this identity. So notice we've got 2k plus 3 times the k plus first case of the left-hand side equals this thing over here, 2k plus 2 over 2k plus 1, and then 4 to the k over the central binomial coefficient 2k choose k. So now what we can do is get rid of this 2k plus 3 on the left-hand side if we times 1 over 2k plus 3. Now what I'll do is start making this look like the right-hand side of this k plus first formula, and that will finish our induction step. So let's see if we can do that. So now I'm going to do a couple of things. So the first thing that I'll do is I'll factor a 2 out of this term. That gives me 2 times k plus 1. But notice if I had an extra 2 in the numerator, I could combine it with this 4 to the k to make it 4 to the k plus 1, which is what we want. So I'll multiply an extra 2 in the numerator, but I can do that at the cost of multiplying an extra 2 in the denominator. Then, like I just said, I'll take this 2 times 2, combine it into 4, and then combine it with the 4 to the k into a 4 to the k plus 1. And then since we really want this 2 to the 2k plus 3 out front, I'll go ahead and bring that out front as well. So this is going to give me 1 over 2k plus 3. So I brought that out front. And now in the numerator, I have k plus 1 times 4 to the k plus 1. That's what I get from all of that business. And now in the denominator, I have 2 times 2 to the k plus 1 times the central binomial coefficient 2k choose 2. Now we just need to manipulate that a little bit more until it looks like this with n equals k plus 1. Now the next thing that I'm going to do is I'm going to take this and multiply the numerator and the denominator both by k plus 1. So let's see what we get if we do that. So now we have 1 over 2k plus 3, and then we have k plus 1 times k plus 1 times 4 to the k. That's in the numerator. And then next, we have 2k plus 2. That's from combining this 2 with this k plus 1. 2k plus 1 times the central binomial coefficient 2k choose k. Okay, fantastic. Now the next thing that I want to do is bring this k plus 1 times k plus 1 to the denominator, but we can do that by taking the reciprocal. So here we have, this is 1 over 2k plus 3. Then we have 4 to the k plus 1 all over 2k plus 2 times 2k plus 1 all over k plus 1 times k plus 1. Great. And then the next thing that I'll do is I'll rewrite my binomial coefficient. So that binomial coefficient is 2k quantity factorial over k factorial k factorial. But now we're home free. We can take this 2k plus 2 times 2k plus 1, combine it with the 2k factorial, and that will give us something that looks like 2k plus 2 choose. We'll look at what we have here. We can take this k plus 1 and this k plus 1 and connect it with those 2k factorials. So we have choose k plus 1. And then next, we still have a 4 to the k plus 1 in the numerator. And then out front, we still have a 1 over 2k plus 3. So let's see what we've got. we've got our k plus first integral of this form is this quotient of objects over here, and this is exactly the right-hand side where we have plugged in n equals k plus 1. Okay, so now we're done with this, and now we're ready to look at this last identity. So we'll go ahead and start with the left-hand side of this and then manipulate it until it looks like the right-hand side. So we've got the sum as n goes from 0 to infinity, 1 over 2n plus 1 times 4 to the n over the central binomial coefficient 2n, choose n, x to the 2n plus 1. Great. Now I want to use our second tool to take all of this stuff, this 1 over 2n plus 1 times 4 to the n over the central binomial coefficient, and rewrite it as this integral of the 2n plus first power of sine. So let's go ahead and do that. So notice here we are replacing this thing that I'm boxing in yellow with the integral over there. So that means we're going to have this sum as n goes from 0 to infinity. Now we've got this integral from 0 to pi halves of sine to the 2n plus 1 theta d theta times x to the 2n plus 1. Great. Now the next thing that I want to do is rewrite this a bit. So I'm going to do that by switching the order of summation and integration, which is allowable because of the dominated convergence theorem. Maybe we'll do a proof of that on another video because we seem to use it quite a bit. And then we're going to notice that something is a geometric series and move from there. So I'm going to go ahead and rewrite this as the integral from 0 to pi halves. And now I've got this sum as n goes from 0 to infinity. Now notice my power of sine and my power of x are the same, so I'm going to smash those together. I've got x times sine theta to the 2n plus 1, and then d theta. Great. Now, like I just said, I want to recognize this as a geometric series where the starting term is equal to x times sine theta. And generally the notation for the starting term is a, so our starting term is x sine theta. And then the common ratio is going to be x squared times sine squared theta. So let's go ahead and notice that as well. The common ratio, which is generally called r, is x squared sine squared theta. So all in all, that's not too hard to see those two parts build up this geometric series here. And then recall that the sum of a geometric series is a over 1 minus r, the starting term over 1 minus the common ratio, so we can write this as the integral from 0 to pi halves. So starting term, so that's x sine theta over 1 minus x squared sine squared theta d theta. Great. Now the next thing that I want to do is take this sine squared and rewrite it as 1 minus cosine squared. Just a little bit of motivation for why we want to do that. We've got a free sine in the numerator. Derivative of cosine is sine, so if we can rewrite the denominator in terms of cosine, then perhaps we can do some sort of u substitution. That's exactly what we're going to do here. So now notice we can rewrite this as the integral from 0 to pi halves of, I'm going to go ahead and call this x sine theta over, so now notice I will have positive x squared times cosine squared. So I'm going to write that as x times cosine theta quantity squared. I get that from taking this negative x and distributing it to this negative cos. And then I have plus 1 minus x squared. But I'm going to write that as plus the square root of 1 minus x squared quantity squared. And I do that because that is going to allow me to recognize this as a u substitution and eventually take a tangent, an inverse tangent antiderivative. Okay, so let's go ahead and make our u substitution. So we can let u equal x cos theta. Notice that's going to make du equal negative x sine theta. D theta, I should say. So let's see, that is going to give us negative, I've taken the minus sign out front, the integral du, so that's the x sine theta d theta is my minus du over u squared plus the square root of 1 minus x squared quantity squared. Now let's talk about our bounds of integration. So when theta equals 0, u equals x cosine 0, but cosine 0 is 1, so that means this lower bound is x. And then similarly, when theta equals pi over 2, u is going to be equal to 0. So we've got something like that going on. Now the next thing that I want to do before we clean up the board and move it to the top is take this minus sign out front, change it to a plus by exchanging the order of integration. So now it's going to be from 0 to x. Okay, so now let's go ahead and bring this up and then we'll finish off this last tool. So on the last board, we worked the left-hand side of this tool down to the following integral that is in terms of u. So now let's go ahead and evaluate this integral. So I'm going to use the fact that I know the integral of du over u squared plus something else squared. So I'll let you guys go ahead and look up that integral. It's kind of well known and could be in the integral chart of the beginning of a calculus book or something like that. So this is going to give us 1 over the square root of 1 minus x squared times the inverse tangent of u over the square root of 1 minus x squared. Great. So that's the antiderivative of that function that is being integrated. And then we need to evaluate that from u equals 0 to u equals x. So I just want to take care of the bottom bound of integration first. Arctan of 0 is 0, so that's just out of here. And so we just have inverse tangent of x over that thing right there. So let's go ahead and write that as 1 over the square root of 1 minus x squared, and then arctan of x over the square root of 1 minus x squared. Great. Now we just have to figure out what that inverse tangent of x over the square root of 1 minus x squared is, maybe simplify it a little bit. So let's go ahead and do that in this little box over here. So we've already used theta as one of our angles kind of earlier, so I'll use maybe alpha for the angle here. So I'm going to go ahead and set alpha equal to arctan of x over root 1 minus x squared. Then I'll take the tangent of both sides, so that means that tangent of alpha equals x over the square root of 1 minus x squared. Okay. Now we can complete a triangle with this data. So we're going to go ahead and draw our right triangle like this. I'll go ahead and point out that this is my right angle. I'll say that this right here is angle alpha. And then I know that tangent is opposite over adjacent. So that means we can have this be length x, and then this right here will be length 1 minus x squared. Now by the Pythagorean theorem, I can complete this triangle and I will find that the hypotenuse has length 1. But now that I've got this completed triangle, I can find all of the trig values evaluated at alpha. And the one that we need for our setup will be sine. So notice that sine of alpha equals x. That means that alpha is equal to the arcsine of x. But notice alpha is also equal to the arctan of this x over root 1 minus x squared. So in fact, we can replace this arctan of x over 1 minus x squared with arcsine of x. But reading this off, we see that it's exactly this third tool. So we just got done establishing this third tool, and now we're pretty much home free. So I've written this third tool back at the top of the board because this is what we need to work with in order to get to the end. So notice that we can rewrite our crazy factorial sum just as a sum of this reciprocal of central binomial coefficients. So we have to kind of think about how to take this left-hand side, which involves the central binomial coefficient in the denominator, and manipulate it until everything else disappears. So in other words, the 4 to the n disappears, the x to the 2n plus 1 disappears, and the 1 over 2n plus 1 disappears. So we can easily get this 1 over 2n plus 1 to disappear by taking the derivative. Notice that this exponent will come down and cancel this guy right here. So let's go ahead and do that. So if we take the derivative of this just using the power rule on all of the terms. In other words, we're doing term by term differentiation of this infinite series. That's going to give us this sum n equals 0 to infinity of 4 to the n over our central binomial coefficient 2n, choose n, and now we have x to the 2n. Great. But now it's pretty clear what we need to do from here. If we evaluate this at x equals 1/2, that will be 1/2 to the 2n, which is the same thing as 1/4 to the n. That's going to go ahead and cancel this 4 to the n out, and we're going to get exactly the reciprocal of our central binomial coefficient, which is what we want exactly. So let's go ahead and do that. So here what I'm doing is setting x equal to 1/2, and that is going to give me this sum as n goes from 0 to infinity of 1 over the central binomial coefficient. But since we're trying to write it like this, let's go ahead and write it as n factorial quantity squared over 2n factorial. Now, since we did all of this to the left-hand side of the equation, we also want to do this to the right-hand side of the equation. So let's go ahead and take the derivative of this right-hand side of the equation. So I'm not going to go through all of the details super carefully, but what I will say is what we are doing is using the product rule, where one of our functions is this 1 minus x squared to the -1/2 power. So I've written the green one like that. And then the other function is the inverse sine function, using the fact that the derivative of arc sine is 1 over 1 minus x squared. So let's see what that gives us. So that is going to give us x times arc sine of x over 1 minus x squared to the 3/2. So again, the -1/2 power turns into a -3/2 power after subtracting another 1. And then the -1/2 that comes down cancels with the -2 from taking the derivative of minus x squared. We still get the x there though. Great, so that's like the derivative of the part in green gives us this right here. Now next we have plus 1 over 1 minus x squared, and we get that just from taking the derivative of arc sine, which is this other part in green. So those combine together to kill a square root. Okay, now next we'll evaluate this side of the equation at x equals 1/2 as well. So let's go ahead and do that and see what we get. So here we are going to get 1/2 arc sine of 1/2, and then over, so let's see, we've got 1 minus 1/2 squared, so that's 1 minus 1/4. So that's going to be 3/4 to the 3 over 2, and then plus 1 over 3/4, like kind of for the same reason we get a 3/4 there. Okay, but now this bit can be simplified. So I'll just put, we're simplifying this thing right here. And along the way, we're using the fact that the sine of pi over 6 is 1/2, which makes the arc sine of 1/2 pi over 6. And after that, it's really just some like fancy arithmetic. And what we end up with is 2 pi over 9 times the square root of 3. So you can kind of see where all of those parts are coming from just by this simplification right here, given this pi over 6 part. And then this is going to be plus 4/3, and that's clearly just the reciprocal of this 3/4 here. So all in all, we have found a final value for our goal sum, and that's a good place to stop.